In this video, we're going to talk about simulation in Fusion 360. Hey everyone, thanks for tuning back in, and we're going to carry on with our lead linkage design, and we're going to focus on some analyzation. We're going to take a look at simulation or finite element analysis and figure out what tools we have access to in Fusion 360. So you want to make sure that you carry on with your design. If you want to make any design changes, then by all means go for it. But the first thing that we really want to focus on in this case is applying some materials. So for our base link, I'm going to right click and select physical material. And then we're going to take a look at the physical material library. We're going to go down to metal. And we're going to just simply apply a generic aluminum. Now the way that this can be done is it can be dragged and dropped onto the body or component in the screen, or we can do it in the browser as well. For this other link, we want to make it aluminum as well. We can drag it and drop it on the body, and then we can close this out. If we go back to inspect and toggle off component color cycling, these now have the appearance of aluminum. So they've changed in appearance, and now we have all the information applied to the component that we need at this point to go into simulation. I do also want to note that material can be applied and overridden in the simulation, so it's not strictly required that it be applied here, but it is a good idea whenever you're making a mechanical design to change those properties at the design level, because it gives you access to things like taking a look at the properties, figuring out the density, the mass, the volume, all these different properties that are associated with your component that are going to be important down the road. So for this design, we're going to use the design workspace, drop down into the simulation workspace. I do want to note that simulations in some cases are going to cost cloud credits. Now cloud credits are given to you at the purchase of your license, depending on what license type you have, when you're viewing these videos, if there's any special promotions. You might be paying $1 per cloud credit, or you might have access to several cloud credits that you can use for whatever you need. So in some cases, things like rendering or certain simulation types will allow you to actually go in and just process things on your computer. But other ones are going to require cloud credits. So things like shape optimization, event simulation, which is still in preview, and electronics cooling. Some of these things are going to require the use of cloud credits. When you select on them, if you want more information or you need help choosing a study, you can select this option. But notice the little icon here that shows the cloud. So not all of those are going to have that cloud next to it. Static stress doesn't, thermal doesn't, event simulation does, and shape optimization does. So anytime you see a study that has a cloud, that's going to require you to use cloud credits to solve. In this case, we're going to focus on static stress, but shape optimization is one that would also be very applicable in this case. Now, shape optimization does cost cloud credits, but I believe it's 5 every time you need to solve. So for this lesson, for these videos, I'm not going to use anything, or I'm going to try to avoid anything that requires cloud credits and focus just on the things that can be solved locally. So now we're inside of the simulation workspace. The tool set that we have access to is different. There's no timeline at the bottom. The browser has changed. It shows simulation model 1, static stress is the study, and then we have parameters in here for loads and constraints, any mesh settings that we have applied. At this point we haven't done anything, so nothing's in there. And this is where we need to start defining it. Now it is important to note that anything that we do inside of the simulation workspace, things like changing the material or making adjustments to the model, they only hold true in the simulation workspace. So anything that we want to change on the design universally, we need to do back in the design workspace. So from here, we're going to go into what's called simplify. If you use this drop-down box, there's only simplify here, but every menu, even if it only has one option, is going to have that drop-down. So in this case, simplify is where we get access to those sketching and those featured tools. However, the tool set does look different here. We have a timeline that's empty. We have a create drop-down, which is different than what we're used to seeing in the design workspace. Even though almost everything is here, we do see some new things like fluid volume. Under modify, we see things like remove features and remove faces and replace with primitives. These are different things that we're not used to seeing displayed in this manner. So the first thing that we want to do is we want to isolate or focus on just one of the components. In this case, we're going to identify the base link as the thing that we're going to want to work on. So I'm going to right click on it and I'm going to remove all except selected. Using remove will keep all of the extra stuff in the design without deleting any references. So remove is the best option that we want to use in here. So now you can see there's a feature in the timeline that shows the removal of those two components, and what we're left with here is the base design. Now the base design, or the base link, is going to be the part that we need to focus on, and we don't really need to do anything extra here. When you come in with more complicated designs, things that might have a lot of tiny fillets or a bunch of additional features that really don't add to the simulation, that's when you want to come in here and really focus on simplifying those, because the time you save in running the simulation and solving is going to be well worth the time you spend simplifying it. So once we're done, we're going to finish simplify, and now we're focused on just this one component. I'm going to rotate this design to my bottom view, and I'm going to focus on adding some loads and constraints. Now in reality, loads and constraints are going to be very tricky for us to just guess at and figure out. There's a lot of mechanical engineering background and possibly some validation that needs to go into figuring these out. So in our example, I'm going to be making up numbers, and I don't want this to convey at all as real world numbers. We haven't even decided what this linkage is for. So I mean, it could be a small robot, it could be some sort of remote control car, it could be whatever. But I just want to make sure that we understand that the definition of loads and constraints is a very important topic, and it requires advanced knowledge of engineering to be able to identify those values. So we're going to be using some values that are just sort of out in left field, but will help us understand how to apply the process. So moving from left to right, we've simplified. I'm going to take a look at materials. Now we can do a few different things. We can toggle on and off the display of study materials. So if we change the material properties from what we have applied in the design, we can make sure that those get updated in the display here. But study materials is the main area where we want to go in and we want to say, well, the material that's applied right now is aluminum. If I want to override that and pick something else, I can come in and choose another material, such as maybe a different aluminum, a 6061 or some sort of high-strength alloy. So that's where all of this would happen. And we can also change the safety factor. In this case, it's going to be yield strength, which is what I'm going to leave it as, but we could also change it to the ultimate tensile strength. Once we're okay with our materials, we need to add some constraints. Constraints are going to be the things that are going to hold our design in place. We have options for bolted connectors and rigid body connectors, and we're not focusing on those at all. Rigid body connectors help us create a rigid connection between vertices on a design, and the bolted connector helps us replicate bolts and preloads without actually having to simulate threads or calculate the strain on a bolt. But for our purposes, we're going to go into structural constraints, which are defined as fixed, pin, frictionless, or prescribed displacement. Again, for simplicity's sake, we're going to use fixed, and we're going to fix the inside diameter of this boss. Now once we do that, we also need to decide how it can move. UX, UY, and UZ fixes it in all three axes. But if we want it to be able to move in the Y direction, then we might want to turn off Y. So this will keep it from moving in X and Z, which is going to be the radial directions. And then if we want to hold it in the axial direction, we would come back and apply another fixed constraint. And in this case, we would say we only want this to be fixed in the Y. So again, it's important that we understand that when we're defining these constraints, we need to replicate how the thing's actually going to be held in the real world. Now ultimately, a design like this, what we would have is some sort of pin constraint allowing it to rotate, But again, we're looking at a very simplified, idealized kind of case because we want to understand how to apply the tools. And I'm not trying to teach you simulation or finite element analysis, but really how it's applied in Fusion. From here, we're going to move on to loads. Now, loads are going to be the force or the stress that's going to be applied to this. So if we take a look at our type options, we have force, which is what we're going to be using here. We have pressure, we have a moment, and then we have things like bearing loads, remote loads, and hydrostatic pressure. Again, the background education or knowledge into defining these is very important and not something that you can pick up by just watching somebody create a simulation case that's similar to yours. You have to understand the loads and constraints that are going to be applied to your design in the real world. In this case, we're going to select force, and we're going to place a force on this bottom link. Now, as we're looking at this, remember that we created that dog link, and it's going to be pointing forward. So I'm going to rotate this at 90 degrees, and then I'm going to determine how much of a load I'm going to apply here. So in this case, I'm going to change the units to something I'm more familiar with. So instead of newtons, we might decide to use ounce force or pound force, and then we can modify that parameter. This again goes back to units, which we talked about earlier on when we were defining the sketch for this part. The units in the simulation workspace and the manufacturer workspace are unique. So even though our design changed to inch, the ratings here in the simulation workspace did not change at all. We can change them. The units right now are custom, but we can adjust it on the fly as well. So I'm going to add a value of 200 pounds here and say OK. A quick side note, fixing the back boss here means that adding the load here that we added, the force, means that there is going to be a twisting or rotating that happens about this pivot point because this force is not in line with this point. So that means that we are creating a moment about this design because we did fix the design or this inside diameter, and we're not allowing it to move. So again, we're looking at an ideal case of just applying some of these values, and we're not focusing on the realistic aspect of setting this study up. I can't stress that enough. I want to make sure that everybody understands that. From here, the next section is contacts, and the contacts are going to be if you're dealing with an assembly that has multiple components. We need to define how those components interact with each other, if they're bonded or welded together, if there's going to be some friction, if they're allowed to overlap, or if they can't penetrate each other. Those are all the things that happen with contacts. The automatic context solver does a pretty good job of analyzing everything, and then you can go back and adjust them. We're not going to worry about the display right now because we don't really have any mesh, but we can toggle on and off the degrees of freedom here. And this tells us that it's potentially fixed. Green would be fully fixed, so if we redefine that first fixed constraint, it would tell us that it was fully fixed. And again, these are things that we need to understand. Is your design fully fixed? Does it need to have some freedom? Is it a limited amount or a prescribed amount of displacement? And these are all important aspects. The next thing that we have is the solve area, and this has a pre-check which tells us that it has all the required information. Each simulation study type will require different information. Certain ones are just going to simply require you to get in and run it. Other ones will require constraints, others might require constraints and loads, thermal loading, things like that. So this pre-check will tell us exactly if we have everything we need. We can solve it, which will automatically begin to generate the mesh based on our just generic settings, and then it'll solve the study. But before we get into that, I do want to take a look at the manage and the settings of our simulation study. The settings are going to be different for each type of study. Some of them will be the same. In this case, for static stress, we have an option to remove rigid body modes. We have mesh settings, and then we have adaptive mesh refinement. Because we're looking at a basic design, I'm not going to be doing any fancy adjustment of the mesh. I'm just going to leave everything as default, but I do want to point out where these options are if you want to make adjustments to them. So now that we have all that information, if you want to pre-solve for the mesh, we can right-click on the mesh and select Generate, which will happen locally on your machine, and then we can view the mesh to make sure the mesh element sizes are okay. Now this is where it comes in real handy to go into Simplify and remove small features like tiny fillets. And right now the mesh is pretty large, but that's okay for what we're doing, so I'm going to leave it as is. The larger the mesh elements in this case, the faster it'll solve for us. So from this point, I'm going to select Solve, and then I can decide whether or not it's going to be on the cloud, which costs 5 cloud credits, or if it can be done locally. Again, keep in mind that not every study is available to be solved locally, and when you're defining the study, you'll be able to see which ones will require cloud credits. All of them can use cloud credits as an option, but these will have certain simulation types that must be solved online. So we're going to solve this. We get a job status, which shows us any uploads that are happening to our data panel, whether or not we're solving any generative designs, which we're not right now, and any simulations that are solving and their status. We can expand this. You can see that it has been sent to the cloud server and that it is currently being calculated. Depending on the geometry in your model, the complexity of it, the size of the mesh elements, these can happen fairly quickly. I didn't speed the video up at all. You can see that happened in under a minute just taking a look at it. This is a relatively simple case, and don't expect all of them to solve that fast. As soon as we solve the simulation study, the results detail will pop up by default. It'll tell us what our safety factor targets are. The safety factor is going to help us determine at what point the design is going to fail. Depending on what the design is, it might require a different safety factor, and ours is above 15, and that's just where it's going to stop. There are recommendations. It can tell us to use other simulation studies like shape optimization to help us remove material. Try testing a weaker material. I'm not really worried about those design improvements. And then we have some options for deformation scale. I'm going to close this, and then I'm going to toggle between different simulation study types. When we go to stress, if we view this from the side, we can see where the original design is, and we can see a deformed scale version of this design. If we want to take a look at the deformation, we can have it undeformed, actual deformation, which is not even able to be seen, and then we can adjust it. Adjusted deformation helps us understand the ways and directions in which our designs are moving and potentially failing. We can also see that we have the max stress in this area. And again, because of the way the study was designed and set up, the constraint holding this back pin or this back inside diameter fixed is causing additional stress that this design would not likely see. But again, it was just for us to take a look at these designs and understand how to work in simulation. From here, we can also take this color bar on the right-hand side, and we can slide it up, and we can focus our attention on specific areas. And one thing we could do for this design, taking a look at these results, is potentially have a large arc in this area that can help spread out that design. We do have a fillet here, but we could make some adjustments to that. We can also take a look at displacement of the model. The max displacement in this case is 0.03 millimeters. And we can take a look at reaction forces, which is going to show us the forces that are created based on our constraints and how the loads are applied. So you can see the reaction force is showing that we have a high stress area inside of this boss. And again, there would be a bearing in there. This would be free to rotate. So this is really not a realistic condition, but it does give us a good idea of what we're looking at. And then we have the strain, which is going to look very similar to the stress in our specific case. And this gives us a good overview of simulation. Now there's a lot more to unpack in simulation. There are results tools in which we can animate the reaction forces in the design. There are different display options where we can actually take a look at the mesh. We can refine it, resolve it, and see if that makes any adjustments. We can also inspect it. For example, we can take a point probe, and that's the max area, but let's say that we want to figure out what the stress is actually at certain points. We can place a point probe there and we can get a good idea. It's 16 here, it's 11.39 here. Once we're done looking at the results, We can use our results tools to create a report if we wish, or we can finish the results, go back into our simulation, and then make any design changes we might want to do. At this point, we've explored quite a bit, so I think this is a great point for us to save the design. And I'm going to go back to the design workspace. I'm going to save my design, and then we can move on to the next video in which we're going to start to explore some manufacturing options for our part.